Yesterday, I gave kind of an overview of quantum mechanics, and I said, really, you don't need to know that overview, but a lot of you may find it useful background information, so that when I say, well, this is what the math says, you have some idea of what I mean by that. Today we'll go into the specifics. This may be review, but the idea is electrons are going to be divided up into energy levels, which are then divided into sublevels, which are then divided into orbitals. And an orbital is like a place where two electrons can live, and it's like a cloud. So when we talk about the shapes of those clouds, one thing that kind of defines the shape, I showed you an example yesterday of a wave function, kind of a really complicated looking one. This one down here. So this is the wave function for a 3D XY orbital. And when the mathematicians look at this, what you often do in math class when you have a function is find the zeros, right? When you're in math class, that's one thing you might say, oh, what are the roots of this function? What are the zeros? So when does this function go to zero? So what the mathematicians do is they say, oh, can we find the zeros of the function? Where does it go to zero? And it turns out they can find two different types of zeros. So we said this is a function of three variables, r, which is distance from the origin, which in our case is going to be the nucleus. And then theta and phi, those are just angles between where the point is in space and the x and y and z axes. All right. And again, it's not critical that you know where this comes from, but it can be a useful like foundation for you to think about orbitals. So places where psi equals 0, that's going to be where you don't find the electron. So if you're trying to draw a picture, if you're trying to draw a map, those can be sort of boundary areas. We call them nodes of the function. And there's two kinds. You can have radial ones. Radial ones would be values of r, where the function goes to 0. So what do we call a shape that is all the points that are a certain distance away from the origin? A circle in 2 dimensions. In 3 dimensions, it would be a sphere. So a radial node is a sphere where electron density goes to 0. They don't affect the shape, though, because they're the same in every direction. Essentially, they have no effect on the shape. And then angular nodes are going to be planes. So it's going to be a certain angle where you don't find the electron. So it'll be planes or cones. And those boundaries essentially set what the orbital is going to end up looking like. Okay. So the idea is we have these nodes. These nodes are kind of boundaries that set where things go. And then this slide, I basically wanted to just reiterate what I said yesterday, that the orbital itself is like a cloud. It doesn't necessarily have an edge. All it is dense where there's high probability, and it's not very dense where there's low probability. So even though we draw a shape for the orbital and we put a boundary around it, that's not a hard boundary. It's sort of like if you have a well-trained dog and you don't have a fence in your yard, the dog kind of knows how far it's allowed to go and doesn't necessarily go beyond the boundary, even though occasionally it could. It tends not to. So, essentially, based on solving the Schrodinger equation and getting the math, there are different types of orbital. All right, we start with s orbitals. So s orbitals are orbitals that have 0 angular nodes. Meaning, at every angle around the axes, they look exactly the same. So essentially, that means they're spherical. And in an s sublevel, there's only one s orbital. So this is an orbital that makes up its own sublevel. And there's an s orbital on every single energy level. So starting from energy level 1 up to energy level infinity, there's always an s orbital. Now the thing is, as you move up from one energy level to another, we said you get further from the nucleus. What that effectively means is that electron cloud gets bigger as you go up. So if you look at the s orbital on energy level 1, it's small. You look at the s orbital on energy level 2, it gets bigger. You look at the s orbital on energy level 3, it gets bigger, and so on. So as you move up in energy levels, orbitals get bigger. And what that means is the electron spends more time further away from the nucleus. And when an electron is further from the nucleus, what does that mean about its potential energy? It's greater. So that's why they're higher energy level. The electron spending more time further away from the nucleus. What else do you notice about those pictures? John? All right, so not necessarily a gap. What's different about 2s compared to 1s? Well, 2s has... okay, so the response is 2s has 1s in the center. Well, that's true, but that's not actually what the drawing is showing. So I want to be clear about this. This second drawing is just showing the 2s. But what's just the basic difference between the two drawings? Yeah, so if you look in the middle, the blue part of the 2s is small. So the blue part in this 2s diagram doesn't represent the 1s. What this is representing is the fact that there's a node a radial node right here in the 2s orbital. So the 2s orbital has a core part where there's some electron density, and then there's a radial node, and then there's another part where there's electron density. So this right here represents a radial node. And I said before that orbitals come from these wave functions. All right? Wave functions have a function can spit out a positive or a negative value. So when you take the wave function and you plug in a point in space, it gives you a value. That could be a positive value or a negative value. We then said you have to square that number, and then that tells you the probability. So what the colors are actually representing in this picture is the value of the wave function, whether it's positive or negative. We call that the phase of the wave function. And it becomes important later on. It's another one of those things, and I know I keep saying this, is another one of those things you're not completely responsible for in this class. But if you have some idea that there's an underlying function that makes this picture, and that function can have a positive or a negative value, that pays huge dividends later on. Because when you combine orbitals, that value becomes important. So the orange here, let's say, might represent where the wave function has a negative value. And then the blue part might represent the region where psi is positive. In terms of the electron probability, that doesn't matter. Why doesn't positive versus negative matter in terms of the probability of finding the electron? Because you square it. So if you square -4 or you square 4, it's still the same number. So that doesn't affect the actual location of the electron. Where it does come into play is when you're combining two orbitals. When you add two functions together. If one of them is positive and one of them is negative, they cancel each other out. But if they're both positive, they add up and become bigger. Or if they're both negative, they add up and become bigger. So it's a detail that I'm pointing out because when you want to combine orbitals, it becomes important. The 3s orbital now has two radial nodes. So the wave function will change from positive to negative. And whenever a function goes from positive to negative, it has to be 0 in the middle. Right? Question? The question was, for your purposes, does it matter if you know which one's positive and which one's negative? No, it doesn't actually. And I arbitrarily chose orange to be negative and blue to be positive. I could have chosen the opposite. A lot of times when we're drawing orbitals, we shade one part of it and leave the other part unshaded, and we say one of those is positive and one of them is negative. Doesn't matter which is which. All that matters is when you're combining two orbitals, the relative signs. So you just need to know, do these two things have the same sign or do they have opposite signs? It doesn't matter which is which. This one here, the 3s orbital has two radial nodes. These are like cut off views. So, we've cut the orbital in half and we're kind of looking inside it. So 3s gets bigger, it has more nodes, and essentially that'll continue. 4s would be even bigger, it would have 3 radial nodes, and so on. Again, all you really need to take away, s orbitals are spherical, and they get bigger as you go to higher energy levels. The next sublevel up are p orbitals. So p orbitals, there are 3 p orbitals in a p sublevel. They have one angular node, so they have one plane that cuts them off in the middle and separates them into two different parts. We call them lobes of the orbital. And so the effect of that is we get these shapes that look like this. You can think of them as snowmen. Oftentimes we draw p orbitals kind of like this, like they're peanuts or propellers. Yeah. The angular node. So an angular node, we said, is a plane or a cone where the function goes to 0. So p orbitals get cut into, have a plane down the middle. So notice this one here, the YZ plane is cutting it down the middle. So it has two different regions. So p orbitals look like this. Now, if there's a node down the middle, a node is where the function goes to 0. So on one side of the node, the function would be positive, say. When you go through the node, you cross that barrier, you're going from positive to negative. So one side is going to have the opposite phase of the other. One will be positive, one will be negative. Remember that just applies to the value of the function, and it doesn't mean that the electron's positive when it's on one side or negative when it's on the other. It's just important for when we combine orbitals. But when we draw p orbitals, we often draw them like this, with one side shaded to represent that. The other thing to know about p orbitals is p sublevels start at energy level 2. So there's no p sublevel on energy level 1. So every p sublevel has 3 p orbitals, one along the x-axis, we call it px, one along the y-axis, we call it py, one along the z-axis, we call it pz. All right. So there's 3 of them there. Same thing holds true with these. They get bigger as you go to high energy levels. So the 2p orbital might look like this. The 3p orbital looks like this. Notice you have your angular node down the middle that separates it into 2 parts. The 2p orbital, or the 3p orbital, you still have that angular node down the middle. What else do you have in the 3p orbital that separates it into different regions? A radial node, yeah, there's a radial node here. But it still has the same basic shape because it has 2 lobes. I love this slide because it reminds me of Super Mario Brothers. And then 4p, even bigger, still has the 1 angular node down the middle, but now it's got 2 radial nodes. This part, especially right there, that mushroom, makes me long for my childhood. All right, questions? The 2 sides, they are always going to be opposite phase. Yeah, so the question was, do the 2 lobes have to be opposite phase? Yeah, if one is positive, the other one has to be negative. The reason is a node, it's just like when you draw a function. If you're graphing like f of x, the function, when it goes through 0, it's always going to go from positive to negative. These wave functions, they never actually hit 0 and then pop back up. So if they go through 0, they're always going to go to the other sign. So anytime you cross a node, this here would be a node, and this here would be a node. If we were looking at a single dimensional function. Yeah, you always change phase when you cross a node. And there's only one other time we're really going to mention phase of orbitals in this class, and I'll point it out then. Otherwise, we're just going to consider the shape. Oh, look, the p orbital has 2 lobes. We need to know that. That's it. D orbitals. Well, let's look at the pattern. S orbitals had no angular nodes. P orbitals had 1. D orbitals probably have 2. And if they have 2 angular nodes, that's going to be 2 planes. That's going to split them into 4 different regions, right? So d orbitals tend to have this 4-leaf clover shape, except for this 5th one over here. That one of its nodes it has 2 cones that are nodes. This last one looks like a p orbital wearing a life preserver around its waist. So the d orbitals have these shapes. There are 5 d orbitals. In a d sublevel. And they start on energy level 3. So in this class, we probably won't use these shapes very much. The s orbital and the p orbital, I'd like you to know their shapes. We use those a little more. When you're talking about bonding, s and p orbitals get involved a lot. D orbitals get involved when you're talking about transition metal bonding. We don't do that a ton in this class, so these shapes aren't that important to you. And then f orbitals, there's actually, well, let's follow the pattern. There was 1 s orbital, there were 3 p orbitals, there were 5 d orbitals. How many f orbitals do you think there are? 7, yeah. So there are 7 of those. I couldn't even fit them on one slide. And I may not have even included this in the notes because these shapes you'll never ever use. These start on energy level 4. And they have different shapes. Like these 3, I think, look like corncob holders. And then you have the exploding blobs. So there's 7 of those, not shapes you need to know. Just kind of completing the picture there. So those are our different orbitals. Let's summarize. S orbitals, number of orbitals in a sublevel. Okay, in S, 1, P, 3, D, 5, F, 7. All right. So since each orbital can hold 2 electrons, what's the maximum number of electrons an S sublevel can hold? 2, 6, 10, and 14. And then starting at energy level 1, 2, 3, 4. In theory, there exist beyond F sublevels. There are more types of sublevels. They're just not occupied. And I forgot to address the big stupidity of this whole thing. And that is, if a normal human being had developed quantum mechanics, what do you think they might have called the 4 different kinds of sublevels? A, B, C, D might have made sense. You know, if you wanted to be fancy, maybe W, X, Y, Z or something. S, P, D, and F, those were chosen because they're the first letters of 4 words that happen to describe 4 lines in the atomic spectrum of sodium, I believe. And so the physicists were like, oh yeah, this is the most logical name we could give to the sublevels. S stood for sharp, and P stood for, I've forgotten, D stood for diffuse, F stood for fundamental. But really, these letters have no significance. They were just chosen at random by people who don't think like normal people. I mean, it's a good thing we have those people to come up with crazy ideas like quantum mechanics, but it would have been nice if they had named it a little better. Turns out that the sublevels after F, so the next sublevel, they decided would be G, and the next one would be H, and the next one would be I. So they got smart only after they decide, only for the orbitals that don't actually ever get filled, so that we ignore it. But if you had another sublevel above that, you would call it G, and then H, and then I, and so on. But it turns out these are the only 4 that are ever occupied in real atoms that actually exist. So, to organize all of this, there's lots of different diagrams you can look at. I chose one. That basically shows all your S sublevels on the left, and then your P sublevels, and then your D sublevels, and then your F sublevels. And this shows them in order of increasing energy. So it turns out it's not necessarily that, you know, all of energy 3 is lower energy than all of energy level 4. It turns out that, you know, energy level 1 is the lowest, and then you have 2s and 2p. Those are lower than 3. Then you have 3s and 3p. Then it turns out 4s is lower energy than 3d. And then 5s is lower energy than 4d, and so on. And so it gets confusing. But this diagram lists pretty much all the orbitals that ever get filled. The way this kind of diagram works is each box represents an orbital. And an orbital can hold how many electrons? 2. So we use arrows to represent electrons. And in each box we can put 1 arrow up and 1 arrow down. The reason we have those gets at something that we don't have to talk about anymore, and that's the spin quantum number of the electron. But essentially, to put electrons in, we would say we'd put an arrow going up, that would be putting 1 electron, an arrow going down, that would be 2 electrons, and so on. So essentially, the way this gets filled up is from the bottom to the top. And there are 3 kind of rules that we follow. One is the Pauli exclusion principle. Essentially what that says is you can only have 2 electrons in each orbital. I'm going to say knowing that name is not really important at this point. It's kind of a holdover from the old curriculum. Luckily, they got rid of this whole this part where you had to memorize what we call the quantum numbers. That was related to the Pauli exclusion principle. The Aufbau principle essentially says we build up from the bottom. Anyone speak German? No. This essentially means build up in German. So you build up from the bottom. You put electrons in at the bottom first, at the lowest energy first, and then fill them up towards the top. And then a third one called Hund's rule. I call it the bus seat rule. So if you were getting on a bus, say to go to New York by yourself, what would you look for in a seat? an empty one. You want one where you don't have to share, right? So electrons are the same way. When they get into a sublevel, they'd rather pick an orbital that they don't have to share. So you don't make electrons share an orbital if you don't have to. All right. So one way to figure out where the electrons are in a given element is to actually use this diagram, count the electrons, and then fill them in from the bottom up. Luckily, we don't have to do that because we have our friend the periodic table. How many electrons do we say fit in an S? 2. Well, what do you notice about the periodic table? Yeah, there's a group of 2 on the left. Like the 2 columns on the left seem to be set apart. Then how many electrons fit into a P sublevel? 6. Oh, do you see the number 6 somewhere on the periodic table? On the right-hand side, the blue part here, there's 6 columns there. That's going to correspond to the 6 electrons that can go in p orbitals. And then we said 10 can go into a d sublevel. This green section in the middle happens to be 10 columns. And then the f sublevel 14, there happen to be 14 columns from this section at the bottom. Section at the bottom, really fits in right over here. This purple section really fits in over here, but that would make the periodic table too long to fit on the page. And so we kind of break it down and pull it out. That corresponds to the F. So we have what we call the F block here at the bottom. Over here on the left, we have the S block. In the middle, we have the D block. And on the right-hand side, we have the P block. With the one exception that helium really belongs in the S block. It's over on the right-hand side because its properties match the properties of the elements over here because they all have filled outer energy levels. But from an electron configuration standpoint, it belongs over on the left. How many people in the room took honors chem? All right. So, do you remember learning like exceptions to the orbital filling rules? Yeah, forget them. All right. If you've learned exceptions to the rules, you can forget them. If you never learned exceptions to the rules, great. Because you don't need to know them. So essentially, when you want to figure out where the electrons are in any atom, you just rely on the periodic table. So the way you can do it is this. The left-hand side is the S block. So whenever you're passing an element in these left 2 columns, you're going to put an electron in an S orbital. Right-hand side over here is the P block. Whenever you're passing an element there, you're going to put an electron in a P orbital. Same thing with the D block, F block, etc. So if you choose an element and you want to know where the electrons are, give the electron configuration. Say I choose phosphorus, which is number 15. I'm always going to start at element 1. Element 1 is hydrogen. So when I pass hydrogen, I'll put an electron where? 1s. Helium, 2s. Sorry, 1s again. So I put 2 electrons in 1s. And then I would go to element 3, which is lithium. That's in the second row in the S block. I'd put an electron in 2s. Then for beryllium, I put another electron in 2s. Now that's filled. I move on to element 5. That's boron. That's in the p block. Second row. So I put an electron in 2p. And I do that for carbon and nitrogen and oxygen and fluorine and neon until 2p is filled. And I would keep going until I reached the element that I wanted. All right. So you use the periodic table, start at hydrogen, count up by atomic number, and just put electrons into place. So for example, all right, oxygen. If I start at hydrogen, I'm putting an electron in 1s, go to helium, that's another electron in 1s. The way I write that is I say 1s2. Don't say 1s squared, because your college professor will make fun of you if you say that. You say 1s2. Next spot I go to is 2s. So I pass lithium, put an electron in 2s. Pass beryllium, put another electron in 2s. This would be 2s2. Then I go to boron. It's in row 2 in the p block, so I'm putting electrons in 2p now. I'm going to put one in for boron, another one in for carbon, another one in for nitrogen, and then I get to oxygen. So that's a total of 4. All right, so it would be 2p4. That's how we give the electron configuration for an element. So take a couple minutes and try and do the next couple. If you don't get to gadolinium, that's okay. And remember, on the first day, I gave you a periodic table, so you have one in your binder, hopefully. Let's do aluminum and iron. We can skip gadolinium. So for aluminum, Alyssa, tell me what you got. All right. You just follow along, you get up to 3p1 for aluminum. Questions there? And then, how about iron? Well, all right. So the tricky part there, when you get into the middle, in the D block, the D is always lagging behind by one level. So 3D comes after 4S. That's basically it. Now, that's a lot to write, especially as you go further down the periodic table. So a lot of times we want an abbreviation. The abbreviation we can use we use the end of each row, the noble gas on the right-hand side, to say, all right, all the electrons up to this, and then add these on top of it. So for example, for aluminum, if I go up one row, from aluminum, the noble gas above it is neon. So I can take the electron configuration of neon, which is 1s2, 2s2, 2p6, and just abbreviate that as Ne, and then 3s2, 3p1. Just saves me a whole lot of writing. And the further down the periodic table you go, the better. So for iron, if I go one row above iron, the noble gas is argon. I can abbreviate all of this up to 3p6 as argon, 4s2, 3d6. So you save yourself a lot of effort by using that noble gas abbreviation. The noble gases always end in something P6. So that's where you cut it off. All right, questions there? And the reason I'm skipping gadolinium, when you get down into the F block now, things get a little weird. Sometimes you put one electron in like 5D first, and then you go into the 4F, and sometimes you don't do that. And we're not worried about exceptions. We want to get the general pattern, and that's it. So just worry about the general pattern. Even on the problem set, there may be some like F block metals that you got to do. Don't sweat them too much. I just want you to have the general idea. Now, what we've been talking about so far are just ions, just neutral atoms. If you have ions, that just means an atom has gained or lost electrons. So if it's a positive ion, you just take away the outermost electrons. If it's a negative ion, you just add extra electrons to it. So for example, if I were going to do calcium 2+, this would be, well, I would start with calcium. The electron configuration for calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So if I make calcium 2+, I would just take away these outer two electrons. And so I'd be left with that configuration. All right, so the question is, can I use an abbreviation for this? Yes, you can. But you might be tempted to just give an abbreviation as like the whole thing being an abbreviation. You can't do that. So you might recognize that this electron configuration is now the same as argon. You can't just write argon. You have to actually go up one row from argon, and you can say neon, 3s2, 3p6. So the electron configuration has to contain at least one electron. For negative ions, you would just add an electron. That one's pretty straightforward. So I won't do those examples now. The one tricky thing I'll mention before we go, for transition metals, when you take away electrons, you actually take away the 4s electrons before the 3d electrons. So iron, we said, was argon 4s2, 3d6. If you were making making iron 3+, you would actually take away these two electrons first, the 4s electrons, and then you would take away one of the 3d electrons. So it would become argon 3d5. That's pretty much it. I might post a little addendum about excited states, electron configurations, but that was the last thing we needed to hit today. Okay, this is just a little addendum to lecture this morning in A block. So I am talking to an empty room, but I wanted to finish off the electron configurations for ions. For aluminum 3+, you would start with aluminum, which is 1s2, 2s2, 2p6, 3s2, 3p1, and then you would take away the last 3 electrons, so get rid of all those. For negative ions, all you're doing is adding electrons, so it's actually a little simpler. So for fluorine, that'd be 1s2, 2s2, 2p5 for fluorine. It's a negative ion, so you add 1, so it's 2p6. For sulfur, you have Let's use the abbreviation. So it would be neon, 3s2, 3p4 would be sulfur. We're adding 2 electrons, because it's -2, so this would be 3p6. And then the last little bit, so far what we've been doing is just the electron configuration for the ground state of an atom, ground state being all the electrons are in the lowest possible energy, like they're on the ground. Sometimes electrons jump to higher energy levels if the atom has lots of kinetic energy. If it's in a hot environment, it might jump to a higher energy level, or if it gets hit by light, it might absorb some energy, jump to a higher energy level. So, for instance, magnesium itself would have the ground state electron configuration 1s2, 2s2, 2p6, 3s2. There's your electron configuration for magnesium. Now, an excited state of magnesium, there are lots of possibilities. So here's the ground state. An excited state of magnesium would take one electron from a lower energy level, move it to a higher energy level. So, for example, you could have 1s2, 2s2, 2p6, 3s1, and then you could promote that extra s electron to, say, 4s, and have 4s1. But there are millions of possibilities. You could promote an electron from, say, 2s to 4s. So you could have 1s2, 2s1, 2p6, 3s2, and then 4s1. So there you're promoting an electron from 2s up to 4s. You could have 1s2, 2s2, 2p6, 3s1, and then you could promote one of those electrons to 187f1. Pretty much anything, anytime you promote an electron to a higher energy level, that would be an excited state. And that's pretty much it for electron configuration. And so you now know what you need to know about electrons. In the next unit, we're going to talk about how the electron configuration relates to the way the atom behaves.